Hey there, we're looking at the triangle inequality today. We first looked at this in our previous lesson about absolute value. Okay, and we discovered this relationship does seem to hold, but why was it called the triangle inequality? Why do we have these absolute values with triangles? Let's see if we can answer that today. The first thing I'm going to do is get rid of this equation because we're not quite there yet. Okay, instead, let's draw some triangles. The first triangle I want to draw here will look something like this. Okay, so here we are, and there's the triangle. Perfect. Okay, so this is what we might call an acute triangle because all three angles here are less than 90 degrees. I could also draw what we call an obtuse triangle. So an obtuse triangle is going to have one of these angles more than 90 degrees. So let me modify this. Let's bring this over like this. Okay, there we go. Now this angle here is greater than 90 degrees. This is an obtuse triangle. We could also have a right triangle, right, where you have a 90-degree angle. I'm not going to bother that. That's sort of in between here. We'll get the point, right? Next, what I want to do is label these sides. I'm going to call this A, B, and C. And same thing on this side. So this will be at my length C, this will be A, and this will be B. So here's what I want to do. I want to compare the lengths of these sides. And essentially what I'm claiming is that the length of side C must be less than the length of A plus B. Okay, this is the classic geometric triangle inequality. You cannot have a third side that is longer than the sum of the other two. That's what the triangle inequality is saying. And let me try and demonstrate why this must be true. I mean, we can kind of see it's true here, right? Like this length C is definitely shorter than A plus B. In fact, A by itself is bigger than C. And here it definitely appears that A plus B would be longer than this length C. Okay, so we can kind of see this, but I want to show you what would happen if this isn't true, right? What if we had a triangle that looked sort of like this, okay? So in this case, I'm going to be labeling this side A, this side B, and this side C. Okay, so the third side here is C. So I'm saying if C was longer than A plus B, this is the situation we would have, right? So this is what would happen if one of the sides was longer than the sum of the other two. Essentially, these two sides would never meet, right? You can't actually touch if this third side is longer than the sum. And so you can't form a triangle this way, okay? So that's sort of the essence behind this. If C was bigger than A plus B, A and B wouldn't touch, you would not have a triangle, and that is why this triangle inequality must hold. Okay, now I want to modify this just a little bit. I want to talk about now degenerate triangles, right? What does that mean? What is a degenerate triangle? Well, what it actually means is it means a one-dimensional triangle. Okay, what do I mean this? Let's take these two triangles that we started out with, the acute and the obtuse, and what I want to do is I want to squish them. I'm going to squish them flat. Okay, so if I take this triangle and I squish it, squish it, squish it, squish it flat, I'm not going to go all the way because if I go all the way, it's just going to look like a line, right? So I'll keep a little bit of dimension there, but imagine I squish it all the way. Okay, now it becomes a flat degenerate triangle. I can do the same thing for the obtuse triangle. I'll squish it, squish it, squish it, squish it flat. Okay, so there we go. It's flat. Let me just move these around a little bit. It's still going to be a triangle though, right? Because what does a triangle need? It needs three sides, and these are still going to have three sides, right? Each of these technically has three sides, even if they're on top of each other. And the sum of the angles should add up to be 180 degrees, right? And that's what happens here. Like this angle goes to 0, this is 0, and this angle is 180, right? This angle is 180, these two are 0. So these are still triangles, even though they would actually just appear to be, a flat straight line. So if we consider degenerate triangles now, well, now things tend to change a little bit with the triangle inequality. Okay, so here we can see that C, this length C, well, that doesn't change too much. So this is still going to be less than the length of A plus B. Okay, so that's the same. But for this triangle, it is different because notice now C will actually exactly equal the length of A and B. And so when we consider degenerate triangles, we actually have to modify our original triangle inequality, because now C is not necessarily strictly less than A plus B, but rather it's less than or equal to A plus B. And so this becomes sort of a modified version of our triangle inequality when we're including degenerate or one-dimensional triangles. Okay, so that's an important step. Finally, let's see if we can wrap this together with the actual triangle inequality we're trying to demonstrate. So in a previous lesson, when we looked at the absolute value of a number, we interpreted that as the distance from the origin to that number on the real number line. I want to reinterpret that now as the length of essentially a line segment, something like that. So let's draw a real number line and show you what I mean. So I'll put the origin here, and then I'm going to draw a point here, and this will be a point A. And how about this will be point B, okay? So what is the distance to point A? Well, I could essentially measure this distance by taking the absolute value of A. A is a negative number, but the distance to point A would then be the absolute value of A. And now I want to reinterpret that as the length of this arrow, okay? So the length of that arrow would be the absolute value of A. That'll give me a positive number for a length, right? Similarly, the distance to point B would be the length of this arrow, right? So I could see the absolute value of B representing this length, okay? So hopefully I can convince you that these absolute values can represent the length here. Irrespective of if the value is positive or negative, we can take the absolute value and get the length of this line segment or this arrow here. So what if we add these two together? Well, if we add these two together, what we're going to get is essentially what we would get if we create a degenerate triangle like this, right? So imagine this is a one-dimensional flat degenerate triangle. I'm saying that this side here is the length absolute value of A. This would be the length of the absolute value of B, and that would equal this side here, which we might call C, right? So what I'm saying is that the length of side C is equal to the length of side A plus the length of side B. And I think that is fairly clear. As long as we're dealing with flat degenerate triangles, this will always be true. However, we can do something else now. We can add the value of A plus the value of B. So here it includes like the sign. And we know that A is a negative number. So what does it mean to add these together? Well, essentially what it means is we will start here at the origin. A is a negative number, so that will bring us down to here. And then from here, we'll add B. B is a positive number, so that'll take us back here. So the sum of what we get here is essentially going to place us at the tip of the arrow here, at this position. So we can represent this as A plus B. And if you want to, you can take the length of that line segment or that arrow. And so the length of that will be the absolute value of A plus B. And if we compare that length to the length of this side C, you're going to see it is smaller, okay? So we're going to say that this is less than the length of side C. Now, why is that? It's smaller because one of these numbers is negative, right? In this case, A is a negative number. For example, it might be -5 plus 3, right? And so when you add A and B, you're actually doing a kind of subtraction, right? If you reverse the terms, you're getting some kind of 3 minus 5. So you're getting a smaller number. When you add the magnitudes, though, when you add the lengths here, that's a true addition. You're going to get a value that spans essentially from the negative to the positive side, something very large. But when you just add the values, you're actually doing a subtraction, so you're always going to get something shorter. And that's why this is always going to hold, because A and B have opposite signs. Now, what I'm going to do here is I'm going to say, well, we know this is true, and we know that the length of C is equal to the length of A plus B. So I'm just going to replace this with the length of A plus B, just like that. And this is going to give us essentially half of the full triangle inequality that we're looking for. And this is true because A and B have opposite signs. Okay, let's take a look at the other kind of addition here that we can be doing. Let me draw you another real number line on this side now. I'll put the origin here, and I'll place point A here and point B here. Okay, so points A and B now both are positive. Let's see what happens, right? So once again, we can define essentially this distance here will be the length of this arrow right here for A. So this will be length A, and this will be an arrow of length B. Okay, so what do we do if we add the lengths together? Well, it would be the length of A plus the length of B will put us at some point here that we can call C. And so what we're doing is essentially creating a degenerate triangle once again. And we can draw it something like this. Again, imagine this is a flat degenerate triangle. What we're saying is that this length A plus this length B would equal this top length C. Okay, so let's write down exactly what that says. We're saying the length of side C is equal to the length of A plus the length of B. And that's if the triangle is perfectly flat here. So this is exactly the same relationship that we had before. Again, this will always hold true for any degenerate triangle, where the length of the two shorter sides equals the length of the third longer side. But just like we did before, we can also add now the values of A plus B, okay? So if we add the value of A plus B, what do we get? Well, A and B are both positive numbers. So if we add A and B, we're just going to get this number C. So this is equality now. While before we have this less than sign, now we have equality because A and B both share the same sign. This is a true addition. This is not subtraction. This is going to be a positive number plus a positive number. That is simply addition. And of course, this will also work if we were to reverse this stuff. So if we were to reverse everything, and imagine here now we had like a negative numbers, right? So if A and B were negative, right? So to the left of the origin, well, a negative number plus another negative number will give us an even more negative number, C. And so this relationship will still hold whether or not A and B are both positive or if they're both negative, just as long as they share the same sign. Okay, so let's flip everything back over again. Just like that. So this relationship must hold. And that means I can take the absolute value of both sides and the equation would, again, still be true. So what can we do? Well, just like we did before, we can see that the absolute value of C, or the length of C, is equal to the length of A plus B. So I'm just going to replace that with the length of A plus B. And now we have the second half of the triangle inequality that we were trying to demonstrate. And this is true when A and B share the same sign, okay? So in general, when you add any two real numbers, A and B, you don't know if they're going to have the same sign or the opposite sign. And so we need to have a general rule that sort of combines these two together. And that's where the general triangle inequality is going to come from, okay? So if A and B have opposite signs, then the length of A plus B will be less than the length of A plus the length of B. And if they share the same sign, then we have equality. And so in general, this bottom triangle inequality will always be true. Okay, so hopefully this gives you some understanding or some intuition on how we can go from a geometric triangle inequality, from normal two-dimensional triangles, and apply that to addition of real numbers. Because we can imagine adding real numbers is sort of like creating a degenerate one-dimensional triangle that lies flat on the real number line, because we can only fit one-dimensional triangles on the one-dimensional real number line. And so when we do that, we naturally get this triangle inequality showing up for the addition of real numbers.